So the problems we do in this chapter usually come down to one of these two equations. The total energy before equals the total energy after, or we relate force to change in energy by saying the work is equal to change in energy and the work is equal to the force times the displacement. For example, a lot of the problems that we did this chapter involved us trying to figure out gravitational potential energy at the top of a cliff, a roller coaster, or something else, and then as it fell, trying to figure out what form of energy it had at each point of the fall, and then solving for height or velocity afterwards. The equation on the left allows us to solve for all the things we need by just setting the energy before equal to the energy after, and maybe the before energy is at the top of the cliff, maybe the after energy is at the bottom, or somewhere in between. If you know that one of the forms of energy is gone in the situation, then you can just cancel it out, and that usually makes life a lot easier because then you can start to set things equal to each other as well as be able to figure out the total energy at one spot and then solve for it another spot along the ride or down the path it's falling. Note that we could also add in other forms of energy to the left side or the right side of the equation. If we wanted to add an elastic potential energy, we could do that, thermal energy, or anything else that's given to us. There can be many forms of energy that are transferred between. Remember the bear problem falling on the trampoline. If we're just looking at energy, the equation on the left should be all you need. If we start to look at force, though, and displacement, then we might need to use the equation on the right. So if you substitute in force times displacement for work, now we have a different way of writing the equation. We could also substitute in for change in energy, gravitational potential energy, we could substitute in kinetic energy, we could substitute in elastic potential energy, really anything we want. In addition, we could also put in MA for force. So this equation can take many different forms depending on the situation. Here I've set work equal to the change in gravitational potential energy, but I've expanded the work equation, or work side, out to MAD, or mass times acceleration times displacement. But make sure you realize that this is a delta mgh, or delta change in energy. That means we can't just call it m times g times height. We have to take the change in height, otherwise our answer might be drastically wrong. So we can expand the equation once more to look like this, where we now have a difference between height final and height initial. Your instructor may actually have written it out like this. They are both saying the same thing in terms of the math, so don't freak out. Either way is fine. Alright, let's try a couple problems that you've already seen before, but maybe if we explain them in a different way, they might make more sense. The first problem is the classic inclined plane problem, which is also what you did in the Making the Grade lab. And this problem, typically what we'll give you is the weight of the actual thing we're lifting up the ramp, the height that you have to take it straight up, and also the displacement that you'd have to take it on an angle. And then we'll ask you to solve for the force that you'd push up on to get that object up the ramp. Here, because we're using force and displacements, your mind should automatically be going to the work equals change in energy equation. Here we have everything we need to be able to solve for the force that we have to push up the ramp with, which I've labeled as F up. Also note that you don't have to solve for the mass of the block if you realize that the force of gravity is really equal to mg, so that would be just two variables that we're going to substitute in for, not just one. After substituting in, we realize that the initial height is 0 meters, so this term is going to go away, and now all you need to do is take 100 times 10 and divide by 20 to get your final answer for force. When you solve for the force, it ends up being equal to 50 newtons. Now, take a couple seconds and think about this. What is the mechanical advantage of this simple machine, the inclined plane? Hopefully, you realize that the mechanical advantage of this is 2. And the reason why is you can compare the forces and see that the weight was originally 100 newtons, and we only had to lift up with 50 newtons of force, which is 2 times less. And remember that mechanical advantage can be solved for by comparing the two forces or comparing the two displacements by taking a quick ratio of the two. And an easy way to remember which one should be in the numerator and which one should be in the denominator is to think about, is this machine making my life easier in terms of force, or is it making it more difficult? Because that's all we're ever doing in any machine, is exchanging force and displacement for work. In this problem, it's making our life easier because we had to only do half the amount of force, so that mechanical advantage should be above 1 and not below 1. If it was equal, obviously it would be a mechanical advantage of 1. Lastly, let's try a conservation of energy problem, and we're just going to go with the exact questions that were in the WebAssign. We've also seen this on the skate park if you're looking for more things to study. Initially in this problem, we're asked to solve for the total energy of the skater on the ramp. Well, we have to know up front that A, B, C, D, and E are all going to have the same total energy. And then the trick to these problems is usually realizing that the total energy will be in all one form at one spot on the track. And if you know that, now you can use that to your advantage to solve for other forms of energy along the ride. So on this track, we know up front that at point A, it should all be gravitational potential energy because he's probably not moving, or if he is, it's minimal at the very beginning. So I'm going to set up my equation and solve for the total energy, knowing that it's all gravitational potential energy at A. After doing the calculation, it comes out to 15,000 joules. The next step we might ask you to do is to solve for the velocity at one of the points on the track. How about position C? In order to do this, we have to realize a couple things. One is that position C is actually our reference or our zero line, which means that all the gravitational potential energy at point A is going to be converted to all kinetic energy at point C, theoretically, as long as we didn't lose anything to thermal energy, and we would tell you that in the problem if you did. So next I'm going to set up the total energy before being equal to the total energy after, and know that it's all in potential at point A, and it's all in kinetic at point C. And since we already know the potential at A, that's 15,000 joules, we can just set that equal to 1/2 mv squared and solve for V. So the velocity is 17.3 meters per second at point C, and now there's usually one more step that we're going to do, and that's typically finding one of the energies or the height of the velocity at some other part of the track. On this problem, it was finding the kinetic energy at E. So in order to do this, we have to think about the conservation of energy again, and the fact that the total energy at point E is still going to be 15,000 joules, and since we know the height, we can figure out gravitational potential energy, and then work from those two to figure out the kinetic energy, knowing that those are the only two forms we should have here at point E. So I'm going to set up my equation as the total energy at point E is equal to mgh at E plus the kinetic energy at E. And the reason why I don't have to break down the kinetic energy equation to 1/2 mv squared is because we're not asked for the velocity. We're just asked for the kinetic energy at that spot. We could also do that if we wanted to solve for the velocity at E, but we just don't need to in this problem. So once again, remembering that the total energy at E is going to be the total energy that it was at A and C, or 15,000 joules. We plug that in, as well as the mass of 100 kilograms, the gravity of 10 meters per second squared, the height at E of 5 meters, and that ends up being 5,000 joules plus the kinetic energy on the right side being equal to 15,000 joules. You subtract 5,000 and you get 10,000 joules of kinetic energy at point E. Now, that should make sense because then there was 5,000 of gravitational potential energy, and the total energy still ended up being equal to 15,000 joules. Alright, that's it from me. This has been Mr. Scott on your Energy Test Review Screencast, and as always, kids, remember to keep calm and show your work.